So a weaker property than second countability is first countability. Second countability said that the basis of a topology has to have, doesn't have to be countable. There is a countable basis for a topology. So again, X is a topological space. And we have defined neighborhood basis. So the first countability says is every X in X has a countable neighborhood basis. Okay, that is given X, and then we have the space X. If I have an open set, there's a basic open set where basic open set needs to belong just to this countable basis. And now you might see quite immediately the theorem, which is if X is a metric space, then X is first countable. So first countable proofs metric spaces may be too big to be second countable, but they're always first countable, and that is because for X in X, in fact, I can take all rational numbers, but this is good enough. Bx of 1 over n in n greater than or equal to 1 is a neighborhood basis. Okay, so this is the first set. And a proposition which is immediate. A basis is a neighborhood basis for all points. So second countable implies first countable. Also, though we are talking about this, I should make a couple of remarks about the last lecture, which I meant to make and didn't make at that point. So you notice that infinity is dense in this, going back to this space, X is R union infinity. Infinity was dense, but if I look at the restriction to R, we get the discrete topology on R, which is not separable because every point has to be in the basis. So it follows that being separable is not hereditary. That is, if I intersect with separable with a subspace, I mean, if I take a subspace of a separable space, it need not be separable. And but second countable and first countable are fairly obviously hereditary because your intersection with a so given a basis, you intersect it with a subspace, you get a corresponding basis for the subspace or neighborhood basis. Okay, so this proposition is almost trivial. Second countable is first countable. So remark, I'll write it here. First and second countable are hereditary. That is, if Y is a subspace of X, then X being first or second countable, whatever property you want, implies Y is the same, whatever it is. But separable is not hereditary. And you can, I mean, if you try to prove it, it's immediate that you'll have trouble, because if I have a dense set and I take a subspace, none of the elements of the dense set may be in the subspace. But as we saw in the just now, the example here is R union infinity with what is called dense point. That was the topology we saw earlier was dense point topology. Okay, so what does this get you? So second countability's consequence we will see later, that regular implies normal, and in functional analysis and so on it has lots and lots of consequences. But first countability leads to something very useful, which is we can deal with sequences. Now sequences have substitutes called nets or alternatively filters. I mean, there are two substitutes which work in general, but often actually having a sequence is important. Okay, so we can use sequences for what? we can use sequences for closure. So first let me define this, and for continuity. So sequential closure. So suppose I have let's see what the result is. So instead of defining it, suppose A contained in X is a subset. Okay, so if following proposition is true, if Xn is a sequence in A and Xn converges to X, which need not be in A but is in X, then X need not be in A but it's in its closure. Proof, well, what do we have to show? Given V neighborhood of X, that's an open set containing X, by definition of convergence, there exists Xn in Xn. In fact, all but finitely many Xn this is true, but you just need a weaker conclusion such that Xn belongs to V. Okay, and as Xn belongs to A intersection V is non-empty. So given any neighborhood of X, its intersection with A is non-empty. So that we saw is a characterization of being in the closure. Yeah, so given any, so this completes the, but what about the converse? The converse need not be true, but it is true if you are first countable. So here's the theorem. If X is first countable, then we have a point X in A bar if and only if there exists Xn sequence in A such that Xn converges to X. Well, we'll just construct Xn. This must be something familiar in analysis, but even if it's not, picture is easy. We construct Xn and we'll take a basic neighborhood. Of course, basic neighborhood need not be nested, but we'll take a countable basis, but we'll take successive intersections of these. They will also form neighborhoods of X, and we'll take points inside the successive intersections. Yeah, so let's say Vn over natural numbers be a countable basis for definiteness. Let me say n greater than or equal to 1, to avoid the issue that conventions about natural numbers having or not having 0 differ a little bit. So let this be a countable basis for or maybe I should just say directly countable neighborhood basis for X. So let's assume X is as above. Yeah, so neighborhood basis for X in X. Okay, with X in A bar. So if we have X in A bar, so suppose X is in A bar, let Vn be a countable neighborhood basis for this. Okay, then choose Xn in intersection I equals 1 to n of Vk, Vi. So I look at Xn which is inside these things. Okay, which is non-empty, Then we can see Xn converges to X. As if W contains in, so suppose we have W open and X, so open in X of course, and X is in W, well then Vn belongs to, is contained in W for some n. That's what, let me put capital N because that's going to be the capital N of convergence for some n. This is just by definition of the neighborhood basis. It follows that for n greater than n, in fact greater than or equal to capital N, Xn is in intersection I equals 1 to n of Vi. Well, this includes Vn. is contained in V and is contained in W. Okay, so for n large enough, we know that, so if we are given any open neighborhood W of x, for n large enough, xn is contained in this, hence xn converges to x. So it was crucial that we could reach in countably many steps to close things up. Okay, because if I had W and it was smaller than all the Vn's, which can happen if you are not first countable, then this argument would not be true. And indeed the result is not true. Okay, so just as we deal with convergence, we can similarly deal with continuity. This is similar to analysis, but it's worth seeing again. It's quite nice. So it's very useful to talk about sequential criterion for continuity. As usual, there will be two sides to it, and one of them is true always. Okay, namely sequential continuity let me just state it. Everything as before, so X is a topological space, not yet assumed to be first countable. So suppose f from X to Y is continuous, so X, Y are topological spaces, is continuous, and Xn is a sequence in the domain such that Xn converges to X. Then, as must be familiar, f of Xn converges to f of X. Okay, for completeness, here's the proof. It's just like in analysis. We have X here, and we have Xn converging to it, and then we have the point f of X. And let's take a neighborhood of this. So let W be a neighborhood. We have to show that this neighborhood of f of x, we have to show that eventually f of xn is contained in f of w. So by continuity, there exists v contained in x neighborhood of little x such that the image of v is contained in w. As xn converges to x, there exists n positive such that if little n is greater than n, xn belongs to v. Hence, f of xn is in w. Okay, and this is unpacked the definition of convergence. So, given any w, we produce a capital N so that if little n is greater than n, f of xn is in w. So this is the definition. For the converse, okay, we need first countability because otherwise you can't probe close enough near a point. Okay, again, so suppose now we don't assume it's continuous. So suppose f maps x to y is a map, and now we say x is first countable. Okay, then one half of this theorem is the proposition above, just like with the previous case. Then f is continuous if in fact I can say at x. This is true at each point, and hence we can have the same corresponding criteria for continuity everywhere. At x in x if for all sequences xn such that xn converges to x, f of xn converges to f of x. So this is the sequential criterion for, I should not claim this is trivial. This is the statement. Sequential criterion is saying that if we know that whenever a sequence converges to x, its image converges to f of x, we know that this is continuous. Okay, so here is a proof of this. Let's see. So suppose not. Yeah, so suppose not. Then let's take a picture here. So let's first of all let W be an open set. Open neighborhood. So an open neighborhood is redundant for us because neighborhoods are always open of f of x. Okay, and let u1, un, etc. be a neighborhood basis of x. So it's not the codomain, only the domain that we have assumed is first countable. So here is f of x, and here's the point x, and here we have neighborhood basis. It need not get smaller and smaller, but we can intersect. Okay, and so suppose f of intersection, I equals 1 to n. Oh, I should just check in the previous page. Yes, it was intersection we took of ui is contained in W for some I, for some n, we are done. Okay, so we are done, meaning, again, I didn't state the hypothesis explicitly. We have to show there is a open neighborhood of x which maps into W, and this is the open neighborhood of W, x, which, okay. Otherwise, pick xn which is in intersection I equals 1 to n of ui, such that f of xn is not in W. Okay. Then, as we saw with the closure, xn converges to x, but there is an open neighborhood of f of x which does not so that f of xn is never in it. Forget about being eventually in it, but f of xn does not converge to f of x. Okay. So I had not said this. We assume this condition. So let's say a contradiction. So this was the main part of the proof. Let me say it again in the full formal sense. One half was already proved. So conversely, suppose that x, we have the sequential criteria for all sequences xn such that xn goes to x, f of xn goes to f of x. We'll show f is continuous at x. For that, we take an open neighborhood of f of x and take a neighborhood basis. And so suppose f of intersection I equals 1 to infinity ui is contained in wi for some n. We are done, because this will be a neighborhood which is contained in W. Otherwise, we'll get a contradiction. Okay, namely, we'll pick a point in this intersection whose image is not in W. So we get a sequence which will converge to X as in the closure case, but the images of the sequence will not converge to W. This will be a contradiction, and hence we must be in the first case, that is, some intersection of the countable basis must actually lie inside W.